Okay, now we're going to look at the stepped or forced response of a first order RC circuit. So in this case, what we're doing is kind of the opposite of what we did with the natural response. We are going to apply a source to a circuit with a zero initial condition. Okay, so we're going to have a switching event, but the switching event is going to add a source, not remove the source from the circuit. So we have a zero initial condition, and then we're going to analyze the voltages and currents of the circuit as the capacitor charges up. So let's look at a simple case, and what we're going to find, as we saw before, that with the step or forced response, a single solution will suffice. And once we have figured out that solution, we don't have to do the solution again, we just have to plug in the parameters. So let's take the following circuit. So we've got a switch that will switch over to this position at time t equals 0. We've got a capacitor value C and a voltage V sub C across that capacitor. So as we've seen before, the thing we're going to focus on is the value across the capacitor, the voltage across the capacitor. Okay, so we're going to assume steady state operation for t less than 0. So again, we're going to make the steady state assumption. And so in this case, if we look for t less than 0, our capacitor is connected. Once again, for steady state, we are assuming that our current must therefore be equal to 0 at steady state, just as we saw before. And therefore, I've got 0 current through this resistor. And therefore, VC must be equal to V0. All right. For t greater than 0, the switch is going to flip. To this position. And once we're in this position, we now have a single loop circuit. This resistor and this source are disconnected. And then we're going to see, let's write a differential equation to see what happens in this circuit. So we're going to begin by assuming that V0 is simply equal to 0 volts. So for t less than 0, I said VC is equal to V0. Let's just let V0 be 0. So that means a zero initial condition. And now for t greater than 0, I'm going to have a current I sub c flowing around that loop. Once again, I'm using the passive sign convention for the current in relationship to the voltage. And so I can write an equation. Vf is equal to IC times R. So it's this voltage plus Vc. And this will therefore be equal to I is equal to C to VdC dt, and so this will be equal to the following. It'll be equal to C to Vc dt times R plus Vc. And I can rewrite terms, and what I will get is that Vf minus Vc is therefore equal to R times C times dVc dt. So a little bit of algebra brought the Vc term over to the other side, and this is what I get. Once again, first order differential equation. So let's rearrange some terms here. And so what we're going to get, let's take the dt, let's bring it over to this side, times RC. So I've got dt divided by RC, so I brought both the dt and then divided by RC. And that will be equal to dVc times Vf minus Vc. And now what I'm going to do is I'm going to integrate both sides. So let's give ourselves some limits here. We're going to assume we know the switching occurred at time t equals 0, so I'm going to write the integrals like so. From 0 to t, d tau over RC is equal to integral Vc of 0 Vc of t at dx Vf minus x. And once again, tau and x are my variables of integration. And now I can go through and I can evaluate those integrals. And so in this case, what I will get is, well, let's do this side here. I'm going to flip these sides around. So I'm going to say that minus the natural log of Vf minus x evaluated from Vc0 to Vc of t. So I evaluated that side is equal to, let's evaluate this side, 1 over Rc, tau evaluated from 0 to t. So dx over x minus x will just be minus natural log. And now I evaluate these two, and what I'm going to get is minus natural log Vf minus Vc of t plus the natural log of Vf minus Vc at 0 is equal to 1 over Rc times t. And now I'm once again going to combine the natural logs together, knowing that the difference between two logs is the same as the log of the ratio of the two values. And so I can rewrite that. And I'll get the following. The natural log of Vf minus Vc of t divided by Vf minus Vc of 0 is equal to minus 1 over Rc times t. And now I'm going to raise both sides to the exponential power. The exponential and natural log terms will cancel, and I'll get the following. I'll get VF minus VC of t divided by VF minus VC of 0 is equal to E minus T over RC. And now I can multiply both sides by VF minus VC 0. And so in this case, what I'll get is VF minus VC of t is equal to VF minus VC of 0 times e to the minus t over RC. And now a little more rearranging. So here, I'm going to rearrange some terms. VC of t, I'll bring the VF over to this side, multiply by -1 on both sides. So what I get is VC of t is equal to VC of 0 minus VF times e to the minus t over RC plus VF. So here's our equation now. We've solved the differential equation that describes the voltage across the capacitor for t greater than 0. But note, VC at time t equals 0 is equal to the V0. That's what we said it was before, which is equal to 0 volts. So really, this quantity is just 0. And so therefore, in this case, VC of t is just equal to VF times 1 minus e to the minus t over RC. And that's what we get for t greater than or equal to 0. This is our first order step or forced response. Now, what does this look like? It looks like this. I start from a 0 initial condition. And then at time t equals 0, I've got 1 minus 1 is equal to 0. But then as t increases, this term goes to 0. And what happens is my output converges to a value of VF. VF is our final or forced value of VC. Hence, we call this the forced response. How long does it take for this to settle to the final value of VF? 5 tau rule of thumb. This settles in approximately 5 tau. Or 5 RC. And we notice here in this step or forced response the same e to the minus t over RC that we saw for the natural response. Same type of exponential response, only now we're charging up to a final value instead of discharging to a 0 value. All right? Now at this point, I could take the tack of working through a lot of problems which would look very much like the natural response problems. But I'm not going to do that because I want to point something out to everybody, and it's this. Remember how before, for t less than 0, I had a V0 value such that VC became equal to V0 for t less than 0. So this is the circuit I had for t less than 0. And I just said, well, let's assume V0 is 0. And that's what I did when I went through and I did this. I just said, hey, let's let it equal to 0. But I don't have to do that. What if I assumed V0 was a non-zero value? Okay, let's consider that for a moment. What if we assume a non-zero initial condition for t less than 0? Well, in that case, I could take that formula and I can keep that VC0 term and I'm going to write it like so. Let's return to our previous equation. I'm going to go ahead and rewrite that. So let's just say VC of 0 is equal to V0. Let's give it some non-zero value. Then in this case, what we get is, once again, VC before and after the switching event, which is equal to VC of 0, is equal to V0. So same thing we've seen before. The initial condition is what persists across the switching event, in which case I can rewrite this equation. And instead, I now get the following equation, that Vc of t is equal to Vf minus V0 times e to the minus t over Rc, which is equal to Vf times 1 minus e to the minus t over Rc plus V0 e to the minus t over Rc. And now I get a really interesting result. Let's look at this equation. This is the general response of the voltage across the capacitor. Or you'll see it called the complete response. Notice what I have here. V0 e to the minus t over Rc, we know what this is. That is the natural response. What do we have here? This is the forced response, which we just derived a minute ago. So if V0 is equal to 0, we have the forced response. But if V0 is a non-zero value, we get this. We get the forced response plus the natural response. And in fact, that is what the general or complete response is. It's nothing more than the superposition of those two responses. So what does the general response tell us? It shows us how we can solve for a problem that goes from a non-zero initial condition to a non-zero final condition. So if I've got this, if I've got a natural response that starts at V0 and decays away, and I add that to a forced response that starts at 0 and charges up to a VF, a final value, and I add those together, what am I going to get? I'm going to get something that looks like this. Get something that starts at V0 and then settles to a VF value after our switching event. And how long does it take to do this? 5 tau. So within 5 tau, we will settle to our final value. Now notice that the initial and the final condition can be any values we want. In fact, if you think about it, a natural response is nothing more than the general response with a 0 final value. A final response is nothing more than the general response with a 0 initial condition. So really, they're all part of the same thing. And all I'm doing here is I'm saying, hey, I can make the initial and the final condition anything I want to. They can be 0 or non-zero, and I can now solve. And the equation I'm going to use will be this equation. This is really the only equation you need. You don't really need the separate natural response analysis we've done before. Really, now that you understand this, you can go through and now use this solution, and you can go through and work any problem, including the ones you just finished previously working. So in this case, what do we need in order to solve? So to solve the general response, first of all, we need to find V0, which is the initial condition for t less than 0 prior to the switching event. So in other words, for t less than 0, I need to find that initial condition. Well, we already know how to do that. We've been doing that before for natural response. Next, you need to find tau after the switching event. And once again, we're going to assume this switching event happens at t equals 0. We've already done these for the natural response. Now we must also find VF. That is the final condition of the capacitor. Okay? Now, in order to find VF, let me point something out. Let's look at this general response. I start at V0, I go to VF. And notice this settles to a final value, and as t keeps increasing, essentially you go to this asymptotic value and you settle at VF. So, as t goes to infinity, VC goes to VF, and something else important happens too. And VC dt also goes to 0. Flattens out, it quits changing. So something interesting happens. We're going to find the final condition of the capacitor as t goes to infinity, and more importantly, and the circuit returns to steady state. So the circuit goes back to steady state. In other words, all the voltages and all the currents, dIdt and dVdt, all go to 0. So all the voltage and currents quit changing. We're right back to steady state, which was where we were before the circuit switched. And this is true as t goes to infinity. Okay, so we're going to need to use a steady state assumption both to find the initial condition and the final condition, because we're assuming the same thing in both cases. Let's work through a problem and let's actually see how this is going to work. Okay, so let's do an example to illustrate how this VF and V0 are found. Let's work the following example. Okay, so in this case, I've got a switch that's going to flip over at time t equals 0. So once again, we're going to assume steady state for t less than 0. And I've got my voltage VC across the capacitor and my current IC through the capacitor. So let us solve for both VC of t and I1 of t. For t greater than 0. All right, what's our approach? Now before, when we looked at other quantities besides the voltage across the capacitor, we had a very simple rule. Find VC first, then find the other quantities, but you can't use the solution. Same thing's true here. We're going to find VC first. Using the general solution. Then find I1 of t given VC of t. So VC of t we can calculate directly using this equation. I1 of t we're going to have to calculate indirectly given the value of VC. So let's go ahead and let's work this problem and let's apply this equation. So let me rewrite this down here. So VC of t will be equal to VF times 1 minus e to the minus t over RC plus V0 e to the minus t over RC. That's our general solution. And now we're going to go through and step by step work this through. All right. So first, let's find V0. So for V0, we want to find the initial condition. So for t less than 0, we've got the capacitor connected here. The current's equal to 0. Therefore, I've got 0 current through this resistor, which means I've got 0 volts across that resistor, which means, therefore, VC must be equal to 90 volts. So my initial condition is just equal to 90 volts. Okay, now, next I'm going to find the final condition. I'm not going to do tau yet. I'm going to do the final condition. So let's find Vf as t goes to infinity. So the switch has flipped over to the other side. For t greater than 0. But now note the current through the capacitor is still equal to 0 because at t goes to infinity, we've gone back to steady state. So once again, IC's gone to 0. So I'm still calculating this assuming there's no current flowing through the capacitor since t goes to infinity. And therefore, in this case, what we get is that if I ground this, and this voltage is VC, and there is 0 current flowing through the capacitor, this is minus 40 volts. Notice the polarity of that voltage source. And I've got nothing but a voltage divider here. And so therefore, VC as t goes to infinity is just equal to 60 over 60 plus 20 times minus 40 is equal to minus 30 volts. And that is my final or forced condition of the capacitor as t goes to infinity. Initial condition, final condition. Now I'll calculate tau. So I'm going to calculate tau for t greater than 0. Tau, of course, is just equal to R times C. C is given, half a microfarad. What's R? Just as we saw before, R must be equal to the equivalent resistance across the capacitor. So let's take a look at this. I want to find the equivalent resistance across this. I'm going to use Thevenin's theorem. First thing I have to do is I've got to zero out any independent sources. That's how you find the Thevenin resistance. So all my sources go to 0. So clearly that's just a disconnected resistor. That does nothing. And so my equivalent resistance across my capacitor must be between these two nodes, the equivalent resistance, which is clearly just 60 in parallel with 20. And so in this case, what I wind up with then is that tau is equal to 0.5 microfarads times 60 in parallel with 20 will be equal to 7.5 times 10 to the minus 6 seconds. So again, that's just nothing but the Thevenin resistance across C. And I can now plug these values into the general solution. And what I will get is that Vc of t is therefore equal to minus 30 times 1 minus e to the minus 13333.3t plus 90 times e to the minus 133,333.3 t volts. Now let's combine my exponential terms. And what I will get is that this will be equal to minus 30 plus 120 times e to the minus 133.3 times 10 to the third t volts. for t greater than or equal to 0. And there's your solution. Now notice, when t is equal to 0, I have 120 minus 30 is equal to 90. That's my initial condition. As t goes to infinity, then the exponential term goes to 0 and I go to minus 30. So just a quick sanity check to make sure I combined these two terms correctly. That should be on my initial, that should be on my final, and when I go through and plug in t is equal to 0 and infinity, that's exactly what I get. So there's my solution. So that's VC of t. What is I1 equal to? Well, let's go ahead back and calculate I1. In order to do that, I'm going to put my voltage source back in. So this is 40. So this is minus 40 volts. I've calculated VC. So I know that the voltage of that node is VC, and therefore I1 of t is just equal to minus 40 minus VC over 20. And I can plug in that and evaluate it, and what I'm going to get is it's equal to minus 0.5 minus 6 times e to the minus 133.3 times 10 to the third t amps. So in this case, I did not try to plug the I1 into the general solution. I found it given VC. So once again, you have to calculate that indirectly. Now once again, this is what I get for t greater than or equal to 0 for I1. Okay? Actually, t greater than 0, excuse me. All right, so here's our results. Okay. Next time we'll come back and we will look at a few more examples, a couple more examples, and just work through these to see how we can solve these problems and to get used to going through these steps of finding the initial, the final, and the value of tau. One thing I want to emphasize, there is only one value of tau. Very common error. Students will try to calculate R for t less than 0 for the initial condition and try to calculate tau for t greater than 0 for the final condition. They'll calculate two different values of tau. No, there's only one value of tau. The only value of tau for the entire circuit is for t greater than or equal to 0. So watch out for that. Again, kind of a common mistake. So we'll come back next time and we'll work a few more examples.